All right, in this video, we're going to be going over resultant and equivalent force systems. So let's first talk about resultant forces. All right, so pretty much all this means is that you're going to sum up all your forces in the x direction, and that will be your resultant force in the x direction. Then you're going to sum up all your forces in the y direction. That will be your resultant force in the y direction. Once you have those two, you can actually make a triangle. So you'd have a resultant in the x and a resultant in the y. Now, if we bring this vector here and just move it over here, we will end up with a resultant y like that. So that there becomes our resultant force, which is just the hypotenuse of a right triangle. So we can then use Pythagorean theorem to find our resultant force. And you'll remember that Pythagorean theorem is a squared plus b squared equals c squared. So if we're solving for hypotenuse, we can just take the square root of both sides. That will cancel, so you'll be left with your hypotenuse equaling that, where a and b is rx and ry. All right, so that's where we get that equation from. And then you can also find the angle theta of this resultant force by just using your trig functions. So we know our opposite and our adjacent side. So we can use the tangent function. So theta will equal a tangent inverse of opposite, which is ry, over adjacent rx. All right, so let's go ahead and run through an example. If this is our coordinate plane here, it's positive x-axis, positive y-axis, and we've got this force A acting at 30 degrees from the y-axis, and it has a magnitude of 5 kips. And we also have this force B at an angle 10 degrees from the negative x-axis and has a magnitude of 2 kips. And we want to find the resultant force and its direction, theta. We're going to go ahead and sum up our forces x, and we're going to call going to the right as being positive. So when we do that, we're going to have ax and a negative bx. So ax is going to be this distance here. All right, now that can be moved up here. So it's that right there. So it's opposite of our angle. So we're going to have our magnitude 5. Now it's opposite, so this is going to be sine of our angle, 30 degrees, minus our bx, which we're looking for this distance. So that's going to be our adjacent side to our angle. So we'll have our magnitude of b cosine of our angle, 10 degrees. Now when you plug that in, you get 0.53 kips, and that's positive. So we know, because we established positive as being this direction, that it's going to be 0.53 kips going that way. All right, so now let's sum up our forces y, and we're going to decide that up is positive. So we're going to have ay, and again, a negative by. And then same thing. So we're going to have 5 cosine 30 this time, because now we're looking for this vertical side, which is the adjacent side to that 30 degrees, and then 2 sine 10 degrees, because now we're looking for that opposite side of that triangle there. And if you plug that into your calculator, you will get 3.98 kips, which is positive, so we know that that's going up. All right, so now we've got 0.53 kips going this way, 3.98 kips going up, so we know that our resultant force is going to be in that direction there. And we can find that resultant force by using the Pythagorean theorem, 0.53 squared plus 3.98 squared. And if you plug that into your calculator, you'll get 4.02 kips. So that would be our resultant force. Now we just need to find our direction theta. So theta is going to be the tangent inverse of opposite over adjacent, which you plug that into a calculator and you'll get 82.4 degrees. Now it's really important that you get your signs correct when you're doing your x and y components, because if you get like a positive x and a negative y, then you'll know that it'll be down here in this quadrant, and so theta will actually be this angle here. So it'll help you figure out which quadrant and where that angle is actually located if you get your signs right on our x and our y. All right, so go ahead and try one on your own now. So if this is your coordinate plane here, you'll have force A at 45 degrees from the positive y-axis with a magnitude of 5 kips and a force B at an angle 20 degrees from the positive x-axis and a magnitude of 10 kips. And then finally, force C that acts along the negative y-axis with a magnitude of 7 kips. And you'll want to find the resultant force R and its direction theta. So go ahead and pause your video, work that out, and then you can check your solution with the PDF found below this video. All right, let's talk now about equivalent forces. All right, so these are very similar to resultant forces, except equivalent forces are going to be acting on like a rigid body, like a beam or a column or something like that, rather than just a particle in a coordinate space like we were doing previously. So Again, though, you're just going to sum up your forces Y or sum up your forces X, whatever forces are on that system, and then you'll find an equivalent force for that particular system. So, for example, if we have a cantilever beam and it's got this rectangular, distributed load, and we'll just say the beam is 4 feet long and that distributed load goes halfway, so 2 feet and 2 feet, and the triangular distributed load goes up to a peak at 2 kips per foot. If we wanted to find the equivalent force acting on that, we just need to come up with that force right there. So we're going to take that distributed load and make it as if it were 1 point load acting on the beam. And so how you do that with distributed loads, you're just going to take the area under the curve of your distributed load. So the area of a triangle is 1/2 base times height. If you had a rectangular distributed load, it would just be base times height. If you had some weird curve that had an equation associated with it, you would take the integral from A to B of whatever that equation is. All right, so let's go ahead and find our resultant force. So that's just going to be our sum of forces Y. And so we're just going to go ahead and take the area of that triangle. So 1/2 base. So it goes along this far, which is this distance here, so 2 feet, times our height of our triangle, which is this here, which is this, so 2 kips per foot. And we run the math on that. We know these 2's can cancel, feet will cancel, so we'll be left with 2 kips. All right, so that would be your equivalent force there. So again, not very much different from what we just did. So go ahead and try on your own. If you've got a simply supported beam, and you've got a rectangular distributed load now, with a magnitude of 2 kips per foot, and then a point load of 10 kips. So this will be 3 feet, 1 foot, and 2 feet there. Go ahead and find your equivalent force R. All right, let's go ahead and pause your video, and you can check your answer with the PDF below. This will be number 2 on that PDF. And that pretty much covers it for resultant equivalent force systems. Go ahead now and take the review quiz until you get 100% on it.